So having covered electronic transitions, let's quickly cover something that's a lot simpler, which are vibrational and rotational transitions. Vibrational and rotational transitions. These are induced by infrared and microwave radiation. So here's what we're going to write. IR and microwaves. IR and microwaves. Notice I'm putting this part in parentheses because it's not going to wind up being as interesting. IR and microwaves cannot induce electron transitions. Cannot induce electron transitions. And this is because their energy is too low. So the energy of the photon is too low. But they can induce vibrations and rotations in a molecule. But can induce vibrations, and in parentheses we'll write and rotations in a molecule. So IR radiation has enough energy to induce a vibrational excitation in a molecule. I will describe that momentarily. Microwaves don't have enough energy to do that, but they do have enough energy to excite what's known as rotation, which I'll briefly describe, but really we're not going to touch this in this class, which is why it's all in parentheses. So what do I mean by vibrational transition or excitation? Well, first let's just cover what vibration means. So in a molecule where we have two or more atoms bonded together, the atoms aren't moving relative to one another randomly. There is a periodic and predictable motion associated with that. And in CHEM we would learn that the motion of atoms is a lot more bizarre than what I'm depicting with my hands right now. But for now, we would describe a vibration as just two atoms, say, moving back and forth in this periodic predictable pattern. But if we give the molecule just the right amount of energy, we can cause the vibration to intensify. This is a vibrational excitation. Give it more energy, we can excite it even further. Okay, so that's what I mean by vibrational transition or excitation. Rotational transitions are similar in that the molecule is rotating about some center, and with the right amount of energy, we can cause it to rotate faster. But again, not a very interesting topic in this class. It doesn't relate strongly to the theory that relates to our analytical techniques. So to tie this with a quick visual, imagine we have our trigonal planar formaldehyde molecule, and those atoms on the outskirts are vibrating like so. And that vibration has some energy associated with it, which we will describe as V0. We could call this the ground state vibrational level, meaning that the atoms are vibrating at the lowest energy possible. And notice we're using a simple line, as we've seen before when we describe energy levels. But then we hit it with just the right amount of energy in the form of an infrared photon, and this happens, a more intense vibration. So the molecule is at a higher energy vibrational level. And the condition for that excitation is the same as what we've been seeing. Whatever the difference in energy between these two levels is, that must equal the energy of the IR photon that's absorbed. And once again, we will convert that unit into one that's more digestible. So instead of thinking in terms of joules or even wavelengths, we're actually going to think in terms of wave numbers, particularly inverse centimeters. And that's what we get for formaldehyde. 2766 inverse centimeter light is absorbed to induce this vibrational transition. And I'm able to do this conversion using this formula that we learned at the beginning of this unit. And as described earlier, this vibration can be excited to an even greater degree. It would just take an even greater energy IR photon that happened to be equal to this delta E right here. And so that's vibrational transitions in a nutshell. Our next goal is to see how this relates to the electronic transitions from earlier. Then we can really get into what's going on in a molecule when light is absorbed. but this is enough for now.